Hello, everybody. Welcome back to another lecture. This week, we're going to be talking about interior construction, and I actually decided to break up this topic into two parts. This module is going to be a little bit longer than maybe some of the other modules, so I'm going to be adding another week onto this. In my original schedule, I think I had allotted 2 weeks to this module, but now I'm going to push it back and make it 3 weeks because there's just a lot of material within this um, chapter or this topic, I guess, that I want to get to between both of the readings. All right, this week we're going to go ahead and read chapter 5 of the Bengali book and then also the interior construction section of the ballast reading that I will have posted to the Blackboard page. This reading will be the same for this week and next week, okay? You don't necessarily have to read it all this week because it will also be assigned next week too, but this week definitely read chapter 5 in the course textbook. The notes from this section are going to be pulled from both, but this week it's going to focus more on the Bengali book. All right. So to begin, interior spaces are defined by the assemblies of several different components that are within them. The term assemblies, that's going to refer to several individual components that come together and form a singular unit. All right, we have a variety of different assemblies that are going to be making up our interior spaces. These can include wall assemblies, floor assemblies, ceilings, and stair assemblies. Okay, but there's a bunch more as well. But basically, these are groupings of structural elements along with finish elements that come together and make a singular unit of something. So a stair, a floor, a ceiling, etc. Now, it's important for us as interior designers to understand the construction of these assemblies because defining them and detailing them is a big part of our job. All right, you're going to be dealing with these frequently, and it's important to understand how these things go together because you're going to be the one going in and specifying the construction of them. Okay, so you're going to be putting in your construction documents basically the instructions that you will give to the builder in order for them to know how they're supposed to put it together. Now, they're going to have an understanding of this as well, but it's important for you to be able to convey an understanding to the builder, okay, so that both of you are on the same page. All right. Now let's begin by talking about some horizontal structural units. All right, so floor systems are supported by structural units such as girders, beams, and joists. This is something we talked about last week. Girders and beams are found in steel structures, and joists are common in wooden structures. All right, so let's take a look at this little image that I have down here. This is talking about joists. So when I'm talking about joists, I'm talking about these, I guess you could refer to them as like beams, but they are horizontal members that span between two supports, okay? And these are what your flooring material is sitting on top of, okay? So this is your main structural support for your flooring, all right? And then over top of these joists, that's where you would install a subfloor, and then you would actually install your finished floor later on. And we'll get more into detail in this a little bit later. But basically, these joists, their dimensions are defined by building codes, and there's going to be specific requirements for them. And their spacing is also going to be defined by codes as well, just depending on the type of structure that it is. If you look down here in this little chart that they have, you can see the spacing requirements for different joist sizes. So you can see here, this column is for 2x6 joists, and then here's 2x8 joists, and then 2x10 joists, and then also the material that they're made out of. But typically, the spacing is one of these three values here, so 12 inches, 16 inches, and 24 inches. And the measurement for this is taken from the center point of each joist. So you'll see it, a term that they talk about a lot in framing is on center. So if you look here, spacing in and then OC, that stands for on center. So that's going to be, for example, if this was like, let's say 24 inches on center, they would measure from the midpoint of this joist to the midpoint of this joist, and that dimension would be 24 inches, and then they would just keep going. All right. Floor and ceiling joists, those have to pass 3 tests. So bending under dead load plus live loads, and then shear under dead plus live loads, and then deflection under dead plus live loads. So all those terms, those are the things we talked about last week. You should have a basic understanding of what all these mean at this point. All right, and then if you want to read a little bit more about this, just refer to this little section right here. So floor functions, floor assemblies must be designed to withstand the intended use of a space. All right, so for example, if you're going to design a floor system for a gym, that would need to handle a lot more weight and stress than the floor of a house. Okay, obviously a gym, you're going to have a lot of heavy equipment, weights and like elliptical machines, treadmills, all that stuff. It's very heavy, so the structure and the entire floor assembly has to be able to accommodate that. Now, if you're at a house, obviously you have furniture and stuff, but it's not going to weigh nearly as much as it would in a gym. So the specific requirements of that floor assembly are going to be lower than it would be in a gym or some other space that is dealing with a lot of weight. Aside from providing structural support, they also need to provide a variety of other functions. Okay, so very similar to like a building envelope, like we talked about in the first and second week. They also have to support fire suppression, acoustical control, thermal qualities. So they're going to have insulation in them a lot of the times. They have to have appropriate surface materials based on their function. Okay, so for example, again, going back to the gym and the house, if it's a gym, maybe it's like a rubberized coating that gives you grip, okay, so you don't slip when you're lifting heavy weight. If it's a house, you might have carpeting material so that there's something soft under your feet. They also need to help control humidity and airflow, and then they must also be sealed in a way that keeps out creatures from getting in from the outside. All right. So floor and ceiling assembly composition. Floors and ceilings exist as a single assembly, and the floor and ceiling components work together to meet specific needs. All right. So what that means is the floor assemblies are built on top of the joists, and then the ceilings are built directly underneath of the joists. And all those things are connected together. So in a way, the floor and the ceiling assemblies are acting as one. Okay, they're all like one solid piece that's built together because they're both directly attached to the floor joists. There are a variety of ways that floor and ceiling assemblies can be built, and the details of their construction are specific to the intended use of the building that they're in. All right. So, for example, one assembly might have a specific thickness, materiality, and like fire acoustical rating, and then you might go to another assembly in another building, and those properties could be totally different, okay? It might be thinner, it might be thicker, the material is going to be different, and the fire rating or acoustical rating might be different too. Assemblies often need to have enough room between the structural bays. So the structural bays, those are the spaces between the joists or the beams to accommodate electrical, plumbing, and HVAC equipment, all right? So within our floors and our ceilings, obviously, we have air ducts, we have electrical wiring, we have plumbing, all right? So the system, the flooring and ceiling system has to be able to accommodate that by the spacing and the way that's put together, so that those things can fit and work as intended. So here's a little terminology for you. Plenum. So this is what's actually referring to that open space that supports the electrical and the plumbing and the HVAC. So that's the open space between the bottom of a floor assembly and the top of a ceiling assembly that's below. I'm going to jump down here for a second. This is 2 pages later. But if you look at this, when I'm talking about a plenum space, this is a cross section of a floor and a ceiling assembly. So you can see here at the top, we have a concrete floor that's on a steel deck. And then here below at the very bottom, we have an acoustic ceiling tile ceiling. Okay. And then all this space, all this stuff between it, that is your plenum. And this is where all of your like electrical and your HVAC ducts are running. So you can see here we have an HVAC duct running through, and then we have some electrical conduits, all that. But when you hear the term plenum, again, that's just talking about all the space between the bottom of the floor assembly and the top of the ceiling assembly that is below it. All right. So back here on the page prior, these are just some good visual diagrams of floor and ceiling assemblies, well, mainly floor assemblies. But you can see here we can take a look at concrete assemblies, steel assemblies, and wood assemblies. So concrete, basically we usually just have concrete slabs, and these are supported by beams and girders. Okay, so we have our grid system here that's going to be supporting those. Steel. Okay, so basically what we have here is a load-bearing wall, and this load-bearing wall is providing support for these joists at one end, and then on the other end we have our columns that are providing support for the beams on this end. And basically we have a series of open web steel joists. All right, so we talked about this last week, but in steel structures usually you have a series of beams that are running across here, beams and girders, or they can be these open web steel joist systems. Then directly on top of your open web joist, you're going to have your metal decking. Okay, so we also talked about that, but that is our corrugated metal decking, and it's kind of like in a U shape or a W shape, but it's just a series of corrugations. So that's installed directly over top of the open web joist system. Then on top of that is where your actual concrete is going to be. And this concrete is either going to be maybe precast, or it might be poured in place. But basically these are the layers that are making up that steel floor system. And then wood, on the other hand, if you come down here, very similar to what we're seeing here with the steel. We still have our load-bearing wall here on the left side, and then that's going to have your joists that are coming across, and they're tying into the columns here on the right side. But on top of this, instead of steel decking, obviously we're going to have our wood decking, okay, which is also known as subfloor. So we're going to have a subfloor that is attached directly to our wooden joists. And if you remember, like I said a couple slides ago, these joists are going to have a specific spacing value associated with them. So is it 24 inches on center? Is it 16 inches on center? Our subfloor, like I said, that is going to be screwed down or nailed down to this joist. And then it will also usually have a adhesive applied to it that is going to also keep it tied down tight to the joist. And we're going to talk about that in a little bit too. But then on top of that, then we're going to have maybe an additional layer, or we will have our finished floor layer. All right. Okay, so interior design concerns for these floor and ceiling assemblies. Understanding floor construction can be especially important for remodeling work. All right, so old structures often need to be modified to facilitate new construction. Okay, so you're going to be putting a new design into it, and in order for the old structure to allow for that, usually modifications have to be made. Okay, so for example, old structures might be constructed poorly or they may have sagged over time, and this requires new structural elements to be put into place prior to the new design elements being added, right? Maybe the new things that you're putting in are really heavy. Again, going back to our gym example, maybe you are taking an existing building, um, maybe it was like a coffee shop or something like that, okay? And you're converting it into a gym. Well, you're going to have to assess that structure because it wasn't originally designed for that purpose. And since it will be taking on a lot more weight now, you're going to have to factor that into the design and probably work with a structural engineer to determine how much more structure do we have to add to the building to support all the new stuff and equipment that we're going to be putting into the new space. All right. So that's all things that you have to think about. So if the function of a space is being changed, the building may have additional structural members to carry the increased loads. So like I said, you're going to be working with structural engineers and building inspectors to determine what modifications a structure may need and how those modifications are going to impact a project's budget. Okay. Old materials may also need to be replaced if they are damaged. So for example, an old subfloor can commonly become water damaged over time, and that can lead to rot and a decrease in structural integrity. All right, so here's an example that I believe they mention in the textbook, but let's say you're doing a residential project and you are, replacing the bathroom. You're going to be renovating the bathroom. So when you pull up all that old flooring material, you may see something like this around where the toilet used to sit. So if something has developed a leak over time, or if it wasn't built the correct way in the first place, you might get some water damage on your subfloor here. So what that's going to do over time is, one, it's not good to be wet, but two, the reason it's not good to be wet is because it's going to lead to rot, and rot leads to a lack of structural integrity, and this flooring material is just going to be brittle and it's not going to be any good, so it needs to be replaced. All right, so these are things that you have to consider whenever you're doing renovations. Are we going to have to factor replacement of existing materials into the project's budget? All right, stuff like that. They're just things that are to be expected with any sort of a project that requires renovation. All right, so floor systems, again, there are different types of them. There are concrete slabs, for example. So these are flooring systems within commercial structures, and those are often made of concrete. Concrete can be poured in place, or a concrete floor system can consist of precast slabs that are manufactured off-site, or maybe they're poured in a different location than where they're going to be permanently installed, and then they're hoisted into place. All right. So precast concrete floor systems are made up of concrete slabs and beams and structural tees. And then they're usually topped off with a reinforced layer of concrete that ranges from 2 to 3.5 inches in thickness. All right, so this is a picture from your textbook, but this just illustrates some different profiles of concrete slabs, okay? So first we have just a flat slab, and then there are ones that have these hollow cores within them. And then these ones are called T's, okay? So they basically form a T shape, so it's a thinner structure on the top, and then it comes down to this T shape at the bottom. This is a single T, and then there's a double T. And then basically what they do is they take all of these panels and then they butt them up against each other over top of the beam and girder system. And so you can see here, if you look at this diagram, we have these control joints that run between them. All right, so you can think of these as the individual concrete panels. So here's one here, one here, one here, and then one here. So those will butt up against each other, and then they will usually put a topping coat over this, like it said previously, that's 2 inches to 3.5 inches. And that's going to be made out of like a reinforced concrete. All right, but these joints between the concrete slabs, just like the brick structures and masonry structures we talked about last week, these allow for contraction and expansion within the structure, and that's going to prevent like failures or cracking to exist in the concrete floor. All right, so if you've ever been in a building that has like big cracks in the concrete floor, usually that's because they lack proper control joints to allow for that. All right, allow for that movement. All right, so wood floor systems. In light frame construction, wood beams support structural planking or decking. Wood joists are made of dimensional lumber. All right, so the dimensions of lumber are something that's called nominal. So you probably heard that term before if you've taken some of the woodworking classes. I think you guys have probably taken furniture design already, but nominal is a term that is often used with dimensional lumber, and this means that they reflect the size of a board when it was rough cut before it was dried and planed. All right, so basically when you have wood that you harvest and then it's going to be processed into lumber, right? They're going to take this and they're going to base the dimensions off of what it was when it was just rough cut before it went through all this processing. All right, and then obviously wood has a lot of moisture in it when it's first harvested, right? And then they have to take that wood and they have to dry it out. So as it dries out, it's going to contract and it's going to get smaller. Okay, it's going to get smaller over time as it loses some of that moisture content. All right, so like this says, as boards are processed, they shrink to their actual dimensions, and the actual dimensions are smaller than the nominal dimensions. So usually this is a half-inch difference, typically with just regular dimensional lumber. So for example, a 2x4 board is really going to measure 1.5 inches by 3.5 inches. All right, and here we have a little chart that's going to show you the nominal dimensions of a lot of typical lumber sizes. Floor assemblies are supported by girders, posts, or load-bearing walls. When penetrations occur in a floor assembly, structural framing members are doubled up in order to maintain structural integrity. So let's say we have a hole that's cut for a stairwell or something like that in our floor. On all sides of that penetration that we were cutting through the floor assembly, they're going to take the joists and they're going to double them up. Okay, so all the structural framing, they're going to have like 2 instead of 1, and that is going to just maintain the structural integrity of the floor system in those areas and prevent those holes from creating like a structural failure. Subflooring, so this is a floor assembly layer that is installed directly over the joists. It can be made from several different materials such as plywood, oriented strand board or OSB, if you've ever heard of that term, wafer board or particle board. Typically, they're 1/2 inch, 5/8 of an inch, or 3/4 of an inch in thickness. I'm a perfectionist. This drives me crazy. I was trying to get the Word document to do the fraction like these two when I was typing this up, but for some reason it just would not accept 5/8 of an inch. So that drove me crazy, but it is what it is. All right, so subfloors, these serve as working platforms during construction, and they provide a smooth base for the finished floor, and they also help to transfer loads to the main structure of the building. Okay, so for our subfloor materials, there are a bunch of different types, obviously, that I have listed up here. And all these different types, they have different pros and cons associated with them. It gets really complicated and technical, but I provided a little link here. So if you want to read about all the pros and cons of why you should use one over the other, go ahead and look at that link and just read it. Read the little article, and that will explain it. And then this one right here, this just shows the process of installing a subfloor. And they kind of explain things about it too, but that's just a really good video to explain the purpose of the subfloor and how it all goes together. But basically, you have plywood, so you guys all understand what plywood is. That's just a bunch of layers that are laminated together. Okay, then we have what we see here on the right. That is called OSB, oriented strand board, and that's basically just long linear strands, okay, hence the term strand board, that are basically cut up and then they are pressed and laminated together. All right, that's very common and it's used a lot, and it's a pretty good material to use, but that could be subjected to, well, one of its weaknesses is the edges. If they get wet, they will like swell up. All right. And then particle board, this is another material, and there's a bunch of different densities of particle board. So you might have heard of a material called MDF, so that's medium density fiber board. That is a higher compacted type of particle board. This one right here that you see, this is a lower quality one. So if you ever have furniture, like cheaper furniture that you get from like the store, like IKEA or something, a lot of the times budget furniture will be made of this like pressed wood, okay? And the problem with that is it usually is not very strong. So when you compare it to something like OSB or plywood, it's usually a lot weaker, and because of that, it can't really hold nails very well. So if you try to nail or screw into this, it would have a tendency to just break apart because it's really brittle. And also, if it gets wet, it's the end. Okay, so if this stuff gets wet, it just basically disintegrates. It's not very, very great. So if this is not used very often, but it's a lot cheaper, so that's one of those things. Some of these materials are better than the others, but obviously with that increased durability and structural integrity, they're going to be a lot more expensive. So it's kind of like you kind of have to weigh the pros and cons, and depending on what the project requires, if there's not as much of a requirement for something that's really strong, and you can save a little bit of money by going with something that's a little bit weaker and not as good, but it still serves the function that you need, that might be just fine. So it's one of those things where they kind of like weigh and they determine what the budget is and what the project needs, and then they will make a determination on what kind of a material they will use. All right. Underlayment. All right, so underlayment is an additional layer that can be installed over top of the subflooring, and that's often made of plywood or hardboard. Underlayment helps spread out the impact of loads, and it prepares the surface for direct application of finished materials that require a smooth surface. All right, so it's just a thin additional layer that may or may not be required, and it just depends on the flooring material that you're going to be installing. So like for example, at my house, I have a engineered hardwood floor that we put over top of the original hardwood flooring that's in our house. So that floor, the original, was like in really bad shape, so we had to replace it with something new. So over top of the original flooring, we put down an underlayment, which was a thin layer of foam. Okay, and what that did was it basically just helps sort of the sound. Okay, so when you put it right, if I were to put the new floor right over top of the old floor, there would not have been as good of a acoustical property between the flooring. So that layer of underlayment, that thin layer of foam, is going to make the acoustical properties of the flooring better. And then also just helps to sort of soften things a little bit. So when you take a step, it just sort of softens the impact. Okay. Subflooring and underlayment are often installed using nails in combination with construction adhesive. Adhesive adds additional rigidity to the floor system and it reduces squeaking. All right, so that one video that I linked above, that shows them installing the subfloor, and you can see in that video how they will put a bead of construction adhesive down on top of all the joists, and then also in the spaces between the panels of subfloor. And then once they have it laid down and attached to the adhesive, they will actually nail it then. And the nails are there to just hold it fast, and it basically acts as a clamping mechanism while the adhesive dries. But the adhesive does most of the work, and the adhesive is good because it reduces the squeaking and it just makes the entire system a lot more solid. Today it's common for wood frame structures to incorporate engineered components like I-joists and trusses. All right, we talked about these last week, but these components are more dimensionally stable than traditional solid wood, and they also often are stronger and lighter as well. All right, so here you can see an example of a wood I-joist. So what they do is they have this top cord here, and then this one is the bottom cord, and that is just regular old lumber. And then they will take a panel of OSB and they will run it vertically between the two. And these are a lot thinner and lighter than traditional beams or traditional joists. But the thing is, they can offer a lot better strength, okay? And they're more dimensionally stable. So a lot of modern buildings are going toward engineered products like this instead of just getting a dimensional piece of lumber, because these are a lot more reliable, and they have a lot of benefits in terms of cost and structural integrity as well. All right. So here's another little diagram that shows a wood floor framing. So you can see we have our wood floor joists that are running across here, and these are sitting on top of like a beam or a girder. All right. And then over top of that is where our subfloor panels go. And you can see that the subfloor panels are staggered. Okay, so that means that the joints don't fall in line with one another. We have a joint here, and then a joint here, and then another joint here. And that just helps to make the overall subfloor system just more solid. It gives it better structural integrity. And then here we have a series of blocks that span between the joists. And the purpose of these is to tie the joists together so that they basically the entire load of the floor system is all tied together at that point. And that will prevent the floor joists from getting deflection. Right, so deflection is basically that like bowing shape in the top of them as weight is applied. These being tied together just offer a greater level of support. All right, steel floor systems. So steel frame structures usually employ steel decking, precast planks, or concrete slab floors. Steel floor systems are often supported by light gauge steel beams or open web joist systems. We've talked about all of this already, but you can see here we have our beams coming across, and then there's that corrugated metal decking, and then on top of that would be our concrete. All right, floating floors. So this is a term that just describes a finished flooring system that is not nailed or glued down to the subfloor. Common examples are laminate or engineered wood flooring. So like I said, I have a engineered wood flooring in my house, and that is a floating floor. So basically we just laid it down and we didn't have to nail it to the wood under it or anything, or glue it down or anything. You just basically cut all the pieces and just lay them down, and then it's done. Okay, so that's what's known as a floating floor because it's not attached to anything below it. It just kind of floats in place. Access floor systems. So these are floor systems that have removable floor panels, and the panels provide access to mechanical and electrical equipment that's underneath of the floor. You're going to see these a lot in office spaces or institutional spaces. All right, wall systems. So wall systems serve acoustical, fire protection, and thermal functions just like a floor or ceiling system. Basically, all of these components that are putting together the building, all right, so floors, walls, etc., all that, they all provide sort of the same types of functions: acoustical, fire protection, thermal, all that. They also partition interior spaces and house electrical, plumbing, mechanical equipment, right, just like the floors do. Load-bearing walls, these are typically constructed of reinforced concrete, metal, or wooden studs. The cavities between the studs are used for thermal insulation, vapor retarders, mechanical distribution, and mechanical and electrical service outlets. All right. Recognizing load-bearing walls is important. It's important for determining whether or not a wall can be removed. All right. I think last week we had a little video on that, how to recognize load-bearing walls. But again, whenever you're doing a renovation, there might be a wall that you want to remove to make the space more open. But if that's a load-bearing wall, it might not be able to be removed. And if it can be removed, you will have to replace it with some other type of a structure, like whether that's a beam or something else, in order to make that open, because you still have to carry that load. So you have to be able to recognize it and know what you need to replace it with. Interior walls and partitions. All right, so these subdivide interior spaces, may or may not be load-bearing. Their construction should be able to support finished materials, provide acoustical separation, and accommodate connections to mechanical and electrical distribution services. So wall outlets for electrical, plumbing connections, all that type of stuff. And the studs within walls are usually spaced 16 inches or 24 inches on center. All right, so just like the joists, studs have a standard spacing associated with them as well. Wall openings. Openings within framed wall assemblies are constructed to allow loads from above to be distributed around the wall openings. This is done by doubling up the structural members around the openings. All right, so here I have a little diagram. This is just a basic framed wall, and here we can see we have a rough opening for a window. All right, so we have our wooden studs. All right, all of these vertical members are studs, and these are spaced usually 16 inches on center. So the midpoint of this stud to the midpoint of this stud to the midpoint of this stud is always going to be 16 inches standard. All right, here at the bottom, this is known as a sill plate and or a sole plate. All right, and that's basically that's the bottom plate that all the studs are sitting on. Then at the top, we have a double top plate, okay? And then we have a series of different types of studs that allow this window opening to exist. Okay, so our king stud, this one and this one here are the outermost studs around the window opening, and these ones go all the way from bottom to top. All right, then we have what's known as jack studs. Okay, so if you look at this jack stud, this is the one directly within the king stud, and that is going to go from the bottom of the sill plate all the way up to the top or the bottom of this header that you're seeing that goes across here. All right, then we have another one over here as well. That's going to go all the way up to the bottom of that header. All right, then we have what's known as a rough sill. So that's these two pieces right here. All right, so then the intermediate pieces between the sill and the header, these are our cripple studs. So these are short little pieces. Those are the cripple studs. And if you look at this assembly, like I said here, anytime you have an opening, they're going to add in all these extra studs in order to double up the structure around the opening, okay? And that just allows all the weight that is coming from above to be transferred around the opening and not be impacted by there not being a stud here in the middle. Okay. All right, now this is the last portion of the chapter, stairs and ramps. So stairs and ramps provide means of vertical circulation through a building, and they can take up a considerable amount of space in a building. Stairs and codes. The design of stairs is regulated by building codes and the Americans with Disabilities Act Accessibility Guidelines, ADAAG. The types of stairs permitted depends on building occupancy classification, number of occupants, use of the stairs, and the dimension of the treads. All right, so you're going to be allowed to use certain types of stairs in a residential setting versus a commercial setting. And then also, if you have a commercial setting, depending on the occupancy type, which you probably learned about in your codes class, that's also going to dictate what type of stairs are allowed to be used. So, for example, like spiral stairs versus straight run stairs or U-turning stairs, all that will be defined within the building code guidelines. All right, if we look at this diagram here, this basically just shows some basic stair parts. So hopefully you guys are familiar with most of these already, but if we take a look at this, basically we have our landings. Okay, well actually the landing is the intermediate basically horizontal plane that exists between two runs of steps. Right, so we have our first floor and then our second floor, and then this is the landing between them. And then any portion between a landing and a floor is a stair run. All right, so you can see we have one straight run here, and then we have another straight run here that gets us up to the top. These supports here on the sides or down the center are known as our carriers or stringers. We'll define those later on, but those are used pretty interchangeably. And these are just supports for the other stair components. They support the treads and the risers. All right, then we have our handrails, and the handrails have specific dimensions associated with them. These are defined by codes, and we'll talk about those too a little bit later on. But yeah, I think that's pretty much it for this little diagram. Next, risers, treads, and nosings. So a tread, that is the horizontal part of the stair that we step on, and they span the distance between two sides of the stair. Treads have to be level and secure, and a proper tread has a minimum depth of 11 inches. Okay, so if we look at this drawing up here, the tread is the flat part. So here's a tread, here's a tread, here's a tread, here's a tread. Usually those have to be at least 11 inches in depth. I think maybe in residential it's 10 inches, but if you're doing a commercial space, that needs to be 11 inches. All right, and that's measured from the back edge here at the riser to the front edge of the nosing. All right, the nosing is the very front edge of the tread. Risers, those are the vertical boards that close off the space between the treads, and they add rigidity to the assembly. All right, so the risers are all these vertical lines you're seeing right here. Boom, boom, boom. Those are all risers. And riser heights typically should not exceed 7 inches in commercial construction, but the height can usually be over 7 inches in residential construction. All right, so whenever we're designing steps, we have to perform specific calculations in order to know how many steps we need and sort of how long our run is, okay? So to do that, you can watch this little video that will explain it. You don't have to worry about it as much nowadays with CAD programs like Revit and stuff, because that does a lot of the calculation for you. You do have to be familiar with the parameters, though, that go into how that is calculated. But this will give you a basic understanding of how to do it by hand. It's really not that hard, so go ahead and watch this. Codes usually require staircases to have a minimum of 3 risers to prevent accidental tripping. So that would mean if I'm building a little short set of steps, if those have less than 3 risers, that it would probably be a code violation. because the idea there is people who can't see very well may not notice that it's a full set of steps and they might trip on them and injure themselves, okay? Nosings, like I said, that's the front edge of the tread. These can have different shapes. Those are also known as profiles. Profile is the shape. So if you look here at this diagram, this is from the textbook. This is the nosing here. You can see this one shows a curved nosing that sort of wraps around at the top. This one's a beveled nosing where you have sort of this angle to it at the bottom. And then you can also have angled risers as well. So the step, the tread, and the riser is basically kind of integrated in this form. So it's all kind of just one piece. All right. And there are specific requirements that go along with these too. They're defined by codes. So for example, the maximum overhang that you can have here over the riser for the nosing is 1.5 inches. All right, stairway widths. Most stairs must have a clear minimum width of 44 inches. With an occupant load of under 50, a 36-inch minimum width may be permitted. So again, this is all defined in codes. Residential stairs must have a minimum width of 36 inches. Egress stairs must have a minimum width of 44 inches. So egress stairs, these are stairs that allow you to exit a building. All right, they're directly connected to the outside. Stairs that allow two people to walk past each other in opposite directions need to have a minimum width of 48 inches. But a width of 60 inches is what's recommended if you can do it. Headroom and landings. So stairways need to have sufficient headroom above them to prevent people from hitting their heads on the ceiling as they walk up or down them. So let's take a look at this little diagram I have right here. You can see here's our minimum dimension of 6 foot 8 inches. And this is going to be measured from the top edge of the nosing, or the front edge of the nosing, to the bottom of the ceiling. So you can see as we are walking, we're approaching the steps, we have our 6 foot 8 minimum clearance, and then that same dimension is what needs to be maintained as you are ascending the steps. So as you're going up, that is a consistent 6 foot 8, and then here at the top again, we have our 6 foot 8 dimension. So here you can see the 2015 IBC codes that requires a minimum headroom clearance of 80 inches measured from the nosing. Flights of stairs cannot exceed more than 12 feet between floors without intermediate landings. So if you are going up 12 feet, or if you're going up more than 12 feet, you have to have a landing somewhere in that stair. Right? So let's say there's 13, like you have 13 feet. You're probably gonna have to put a landing in the middle of those steps then, just because of codes. Okay, so you would go up like 6 feet and then have a landing, or you go up 7.5 feet, have a landing, and then go up another, 13.5. No. 6.5. Man, my math is terrible today. So you go up 6.5 feet, and then you'd have a landing, and then you go up another 6.5 feet. Okay, so you have to have that by code. Structural landings, or stairway landings, should be designed to integrate with the building's structural system to avoid framing complications. And landings must be at least as wide as the stair width and a minimum of 44 inches in height measured in the direction of travel. In dwelling units, a minimum of 36 inches is allowed, and according to the IBC, landings serving straight run stairs need not be longer than 48 inches. All right, handrails. Handrails are barriers that are made of horizontal rails that are supported upright, or they're supported by uprights called balusters. A rail that with supporting balusters is called a balustrade, okay? So let me see if okay, let's go back to this example. These are our balusters, these vertical pieces right here, and then obviously our handrail. The entire thing as it exists as a single unit is a balustrade. Handrail requirements are specified within building codes and may vary depending on the stair's use, right? Just like all these other requirements, the codes are going to tell you what you need for a handrail depending on what it's being used for. Handrails must be free of sharp or abrasive elements, and they should return smoothly to the wall or downward to the walking surface. The shape of handrails should be circular for commercial stairs. Rectangular handrails are not permitted because they are more difficult to grasp. All right, stair types. So we have a bunch of different types of stairs, obviously. They can come in a bunch of shapes and sizes and forms. Stair types can come in many forms. Below are some of the common types. Straight run stairs, so that is just a straight run of stairs, right? Just like you're probably most used to. Here is a quarter turn stair. So this is a stair that has a run that goes up, hits a landing, and then turns 90 degrees. The two flights may be unequal. So this one is obviously, this flight right here is longer than this one right here. Half turn stairs. So these are ones where you go up and then you're basically doing a 180 and going up this way then. These are also called like U-turn stairs. I think in Revit, if you're creating a stair, that's called a U-turn stair. Then we have winding stairs, okay? So winding stairs are similar to quarter turn stairs, except instead of a landing that you're coming to, as you are turning this corner, you are continuing to go upward, okay? So the landing is basically divided into a series of steps itself, all right? And then curved stairs, it's just a stair that curves upward. And then spiral stairs, okay? So a spiral stair, they have very small footprints, but you're basically going in a spiral all the way up. And usually these are not allowed in like commercial environments. They have a bunch of like strict requirements around them where they can be used. They're, I think, more of a novelty probably just because they look cool. But, well, and also for spaces that are really tightly confined where you can't fit like a traditional staircase, you might use a spiral stair just because they're so small. If you look at them in plan, their footprint is not very big at all. All right, so wooden stairs. Wood stairs are supported by stringers or carriages that serve as inclined beams. Stringers are the structural members that support the risers and treads from beneath or at the sides. May also be called carriages. The two terms are kind of interchangeable. So if we look at this cutaway diagram, this is basically what you should think of when you hear the term a stringer. So you can see there's a series of stringers here, and the stringers are notched to support the treads and the risers. Okay. Steel stairs, very similar to wood stairs and have the same components. Everything is just made of steel. Components are pre-engineered and prefabricated. All right, so that means you're not going to be putting them together on site. They're going to be shipped in, and then you will assemble them there on site. Treads are usually concrete, filled pans, bar grating, or flat plates that have textured top surfaces. The underside of steel stairs may be left exposed, or it can be finished with gypsum board or metal lath and plaster. Concrete stairs, these are very heavy and require careful structural design, and they are reinforced with steel. They're also, the finish on the top is a slip-resistant nosing and treads. All right. Exit stairs. Stairs defined by code that allow for means of egress from buildings. Exit stairs are contained within an enclosure, so that would be also known as a stairwell, and the enclosure must meet specific fire rating requirements. Doors within exit stairwells must swing outward, so they swing out toward the outside in the direction of discharge. So the direction of discharge being the direction that people are, leaving the building. And the reason for that is just to make it easier. So if there was an emergency, obviously you won't want to stop and like pull the door toward you. You can just use the crash bar and kind of run into the door, and it just opens and you can run out very easily. Ramps. So ramps are a sloping floor or walk that connects two levels. Stepped ramps are ramps connected by a series of steps, A helicline, that is a curved ramp. Ramps are designed to make travel from one level to another smooth and relatively unobstructed. They require long runs. If a ramp is too steep, it can make it difficult for people with mobility issues to use them. Wheelchair ramps are limited to a rise of 1/12, but more comfortable to use one with a 120 rise. So what these numbers mean are for every 12 feet in length that the ramp has, you're allowed to go up 1 foot. Okay, so I'm walking 12 feet in front of me, and by the end of me completing that 12-foot walk, I have now elevated myself 1 foot in the air. Okay, so as you can see, if you're only going upward 1 foot for every 12 feet that you walk, that means that these ramps are going to have to be really long. So if you're doing if you're going up 3 feet in the air, if the door is 3 feet above the ground level, then that's going to be 36 feet in total length of the ramp. So they're really long and they take up a lot of space, but that's what you need when you are doing wheelchair ramps for accessibility. And they even say a more comfortable one to use, if you can, is a 120. So instead of 36 feet, you're now looking at, 36 feet, you're now looking at 60 feet to get there, to just move upward 3 feet in the air. So they have a huge footprint to them. Ramp landings, these are defined by ADA requirements, but ramps have to have level landings at least 60 inches long at each end. Inserting long landings allows ramps to wrap back on themselves, which saves space. Okay, so if we look at this here, you can see we have this landing on this side, and that is what allows us to wrap back this way, and it condenses the overall footprint of the ramp. But if you look at this is just a basic example of a ramp that you might see somewhere. And as you can see, we're only going up like 3 feet in the air, but to accomplish the same thing that these stairs are doing, we have to have this massive ramp to get to the same level. All right, so it just takes up a lot of space. So you have to have enough room for them. Ramp curbs, guards, and handrails. These are required to keep people from slipping off of ramps. The specific requirements are defined within the ADA design guidelines. Handrails are required along both sides of ramps with a rise over 6 inches or a run greater than 72 inches. According to the 2010 ADA, the top of the handrail should be between 34 inches and 38 inches above the ramp surface. And handrails should extend at least 12 inches horizontally behind the top and bottom of ramp runs. All right, so that is going to do it for this video. Please take a look at the material in the textbook, read through it all, make sure you understand it, and if you have any questions, don't hesitate to email me or text me.